Good morning, dear all. So we are waiting a little bit for another attendee to shift Zoom from one talk to another. And in the meanwhile, I'm happy to introduce the next speaker, Dr. Mahmoud Mazarji. So he's a senior researcher in Academy of Biology and Biotechnology of Southern Federal University. So he received his PhD diploma in environmental engineering from University of Tehran. And his main research field is exploring nanomaterials applicability in soil remediation processes. Specifically, he is researching the absorption and different advanced oxidation process in the remediation of PHAs and heavy metals polluted soil. And today he will present his talk, Potential Application of Metal-Organic Frameworks in Different Remediation Technologies. And I would ask Mahmoud to first start the slideshow and then share the screen. In this case, we will see your slides. Okay, so we can see your slides, but we cannot hear you yet.
Okay. Hello, everybody.
Please, the floor is yours.
Thank you, Mikhail. Welcome to my talk. As Mikhail introduced me, I am Mahmoud Mazarji. I am the postdoctoral researcher at Academy of Biology and Biotechnology at South-Dakota University. I am so opportunate to work with Professor Minkino as one of her postdoctoral researcher. And today I want to present my talk about potential application of metal-organic framework in different remediation technologies. A little brief introduction again, sorry for repeating. I got my PhD degree from University of Tehran in the field of environmental engineering. And from that moment, I work in water and wastewater treatment. And after joining Professor Minkino group, I started working in the soil science. And today it's mostly my experience working in different media and with a different remediation technology that I want to present. My presentation is in the 6 bullet points. First, I will have an introduction about metal-organic framework. Then I will present about the diversity matrices about the metal-organic framework. Then I introduce you with a remediation technology that they are based on metal-organic framework. Then I talk about current application. At the final stage, I will talk about the potential application of metal-organic framework in soil science. Here, you can see the metal-organic framework structure. It's consumed from the 1 metal ions and 1 organic linker that they are repeating over and over until we have this material so far. And I should tell that this material is a hybrid organic and inorganic, that they can offer us easy chemical tunability. Since we can change the metal cluster and combine it with any organic linker, we can have so many diverse metal-organic frameworks. And this structure, it has a crystallinity, and it's a very advantageous from this structure that it's different from other hybrid organic and inorganic material. And the third advantage that they offer, they have a porosity. And not only we can construct a different structure with crystallinity, we can have a porosity exact with a different structure. So since they have a very high porosity, they are having a large internal surface area that can be very good at different remediation technology. At the end, we have a possibility synthesizing this material with exactly tailored properties. That's very important because we should have addressed different remediation from the different target pollutants. Metal-organic framework, they are they can be used as a sensor, drug delivery, gas absorption and storage, and one of their application can be remediation that today I want to talk about mostly. Here I collect some brief introduction from the Scopus about the different statistics this material have. You can see here, this is a graph that shows the publication per each year. And you can see even COVID-19 couldn't decrease the trend increasingly that this material shows. And during the 2021, it's almost 8,000 paper has been published on the subject of metalorganic framework. So that is very promising field that we can invest a lot by publication and having a lot of citations. And here, this is a by subject pie diagram that you can see mostly chemistry people working in different structure that they want to offer. Then material science try to engineer this material, and then chemical engineers start using them as and find their application. And here, this is very interesting. I collect this data last week, and you can see that China has almost 25,000 paper. Then United States, you can see they almost a half of China, and then other rest of the country, they are almost publishing 1,000 per 1,000 papers total. And you can see here, Russia is very low, only publishing 1,000 paper. I guess organization and funding agency here needs to look at this graph and try to address this problem to see the Russia among the top countries that are publishing a metalorganic framework. Here, you can see the brief introduction about the different remediation technologies that they are based on metalorganic framework, and we have a potential high chance of the remediation. First reaction, we can talk about the Fenton-like reaction. Mostly metalorganic framework they have been using for catalytic application. Then the second remediation technology that mostly paper focus on is photocatalysis, where we have a photocatalytic material. Then the third is sulfate radical oxidation, that we can activate the sulfate radical for remediation of organic pollutants. And the last one is the adsorption that has been mostly occupied by many researchers and publishing many papers for in this as an application of metalorganic framework. Here, this is a pyramid of metalorganic framework, and the base level of this pyramid is talking about the diverse contaminant interaction. All of these remediation that I mentioned, they are mostly surface-facing remediation. So if we don't have an interaction, we have nothing. Since metalorganic framework, they can have different interaction with different organic and inorganic pollutants, we have a high possibility of the targeting them and cleaning the different media. We can include the high surface area, they can trap the pollutants easily, and the high porosity, that there are advantages during all these remediation technologies. The next level of this parameter that we should consider about the photocatalytic activity of this metalorganic framework. Because they have a narrow band gap, they can easily activate it during the solar light irradiation. So this is very advantageous during the photocatalysis or photophenton-like reaction, where we can activate them by the sunlight. And also they offer tunable surface chemistry, where we can add other guests inside the structure and make this band gap also become narrower and become more active. The next level that we should get a lot of advantage of this metalorganic framework is ease of use and ease of reuse. That is mostly in all of remediation. We don't want to spend our material inside the reaction wasted. We should collect them and start using again. This is the highest level of this pyramid is about the high chemical stability, that this material can withstand during the different reaction and different cycle of the process. So we can have them still intact and can use them during the different reaction further. So here in this slide, I want to talk about the current application of metalorganic framework. We have a lot of papers publishing. I just select some of them based on this remediation technology that I introduced you in the previous slide. It just started from 1989 when the first metal organic framework has been introduced. Thereafter, we had many papers and it still is going on. The first example is the absorption when this metal organic framework offered the selectivity to absorption process. Because we cannot have an unselective reaction. We should now in 2021, we should forget about unselective absorption. We should target exact each pollutant and remove them from the solution. And from the research paper that I see, metal organic framework offered a high absorption capacity during the absorption of different radionuclides material. And here is the example. You can see that the researchers start using Z, and you can compare the absorption capacity with normal activated carbon or zeolite. So the absorption capacity is almost 8 times higher. So it's just justified the use of this nanomaterial inside the removal of the arsenate from the solution. The next example is a phenton, where we have mostly MIL material using as a catalyst during the reaction. The phenton reaction is where we need to activate hydrogen peroxide. This is the MIL 101 based on chromium, and you can see it easily activated during visible light and can decompose hydrogen peroxide to a hydroxy radical, then start targeting organic pollutant inside the solution or any other media that we have. The third example is a photocatalytic reaction, where we should have the tuned structure of metal organic framework. Usually MIL, again based on the iron, has been used, but we should use some trace element to adjust the band gap they have so they can be activated during the lower photon energy, and then they start producing hydroxyl radical by oxidation of the water molecule, then other superoxide anion radical at the top of the conduction bond, and then start targeting different organic pollutants. And the last one that has been like a subject of using a lot of metal organic framework different structure is a sulfate radical oxidation, where we have a persulfate and we have to activate it by the different catalytic metal organic framework. And one of them, again, example of MIL 101 based on the iron, they can activate persulfate, produce a sulfate radical, then target the organic contamination. So the future is still going on, and I believe that it still needs to, a lot of aspects needs to be addressed by many researchers. This week we had a World Soil Day, and I'm working in the soil science group. I want to talk about potential application of metal organic framework in the soil remediation. You know, from these many papers that you see during the diversity mix research, nobody target using metal organic framework in the soil. So you can see the huge gap that the researcher prefer to go for the gas or the water media and not to touch the soil. So here I want to present why soil is completely different media that nobody wants to go for it by use of metal organic framework. In the soil, we not only have the organic material inside the soil, usually organic content, we have a different structure like a clay material. We have a mixture of the pollutant unwanted to bond with different part of the soil. For example, we have a heavy metals. Then in the other side, we have an organic contamination like a polycyclic aromatic hydrocarbon. And we can say the polycyclic aromatic hydrocarbon, they can bond to the humic acid and make the complex different media that cannot be touched by any typical radical oxidation, and we need to adjustable material completely to target this pollutant inside. So it was, I think, why researchers don't want to go for using metal organic framework in the soil science. As a one group pioneer using this metal organic framework, we start synthesizing MIL 101 based on the iron. Why we choose iron? Because in the soil, we don't have any standards limiting the use of the iron. So MIL 101 iron, if it stay in the soil, is not going to be secondary pollutant. So it was our choice. So we started researching using MIL inside the soil. Then we just afraid if we use the metal organic framework directly in the soil, because the soil is completely, the pollutant has been not distributed evenly, and there is a less chance to metal organic framework have a chance to contact with the pollutant. That's why we also thinking about the price of the metal organic framework. So these criteria we put together, that's why we decide to composite our material with biochar to reduce the cost and also take advantage of the synergistic effect between biochar and metal organic framework. So it was the second step that we decided to composite our metal organic framework with biochar to introduce our material inside the soil. So you can see the same photo of the composite that we synthesized. You can see here is biochar, and you can see MIL 101 evenly distributed on the surface. So it was our strategy to be the first group of the researchers to use the metal organic framework in the soil remediation. So here in this slide, I want to just present the roadmap that how we design our experiment to see the efficiency of our material. Here you can see this is our biochar surface based on the scanning electron microscopic. You can see that it has a lot of porosity, and it can offer us very good advantage of targeting many pollutants. And here, this is our metal organic framework structure, SEM and TEM picture. You can see the octahedral structure that they can easily visible by their microscopic image. Here you can see the same photo that we had synthesized successfully, and here you can see the XRD of our material. Here we use a rice husk biochar since it offers a very good cation exchange on its surface, and it can be a very promising material for taking heavy metals. Then here, this is a structure MIL, and this is a structure of the composite. You can see the structure is still, the XRD pattern show the same peaks, so it means that adding the biochar inside the composite didn't destroy any structure of MIL. Also, I calculated elliptic crystallinity has been decreased, so it means that the size of particle has been reduced. MIL size is a little bit smaller, slightly. Here, this is the TEM photo. You can see the biochar has been used as a guest to grow the MIL in top of the edge, and here you can see one of the porosity that the biochar has, and the metal organic framework has been grown inside. And here is a short video of the TEM that we had with biochar, big particle of the biochar, and the MIL. You can see that they are growing. They have been grown on the edge of this particle. And the last one is a small leaching column that we designed for specifically using to see the performance of our composite inside this column. And the soil that we use, it's a real contaminated soil taken from one of the highly polluted industrial area in the Rostov-on-Don. So the pollutant that we had inside is mostly heavy metals and the polycyclic aromatic hydrocarbon. So this mixed nature of the pollution, it just allows us to have a different data collected based on the each daily leaching that we collected from the columns. Next slide. Here you can see the schema experiment that we had. We leached the column with dionyls that had a pH of 5.5. Why 5.5? Because we wanted to simulate the acidic rain having on the top of the soil. So you know that this acidic rain can mobilize heavy metals from the soil and goes to the groundwater. And also it can activate the low molecular weight of the polycyclic aromatic hydrocarbon to go to different deeper profile of the soil. Here, this is the schematic of our column that we had this real contaminated, then we add a different dosage of the MIL composited with biochar. And each day we collect the leachate from the column and we analyze based on the heavy metal and polycyclic aromatic hydrocarbon. Here you can see the 3D graph that we had for the removal of the Cooper. This is the result for biochar, and this is the 3D graph of the composite, that how the Cooper has been leached through the different conditions that we had. The first concentration we saw is started from 3, but the composite it's almost 1.5. So it's like the half decrease. And also the trend that you can see here, the trend of the composite has a less concentration, and it shows that the composite having the better performance compared to the biochar. But the result maybe is not interesting in terms of the removal of the heavy metal, but when it comes to the removal of the polycyclic aromatic hydrocarbon, we got a very good result. Here you can see that 1 gram of the biochar, it almost removed 5 microgram of the polycyclic aromatic hydrocarbon. And I should explain that this is not a removal, it's like a retention. So this solution that we collect, it means that it had less polycyclic aromatic hydrocarbon, and it means that the biochar fixed the leaching of these polycyclic aromatic hydrocarbon from the column. But once we had a composite, it's get a better performance, and we had a 3 times improvement in retaining the polycyclic aromatic hydrocarbon compared to the biochar. So the composite, it just justified its usage inside the soil. Here, I want to present in my last slide the proposal about the mechanism that we had during our experiment. Here, this is a schematic. This blue color represents the biochar, and this octahedral structure presents the MIL that we had. And this is a Cooper, and this one is a polycyclic aromatic hydrocarbon, and their benzene ring. And we had a different low molecular weight, high molecular weight, and medium weight molecular weight. So we had all different structure of the polycyclic aromatic hydrocarbon inside the soil. First, we should see here the biochar gives us the advantage of the cation exchange. So it means that Cooper can easily, be exchanged with calcium and magnesium on the surface of the biochar. And we can have an electrostatic interaction for removal of the heavy metal, since the surface of this material offer a lot of negative functional group. So it means that they have a lot of carboxylic acid, ketones, and different negative functional group that they can offer the very good interaction with our heavy metal. And the pi-pi interaction, we can say that only MIL-101 offer in the composite. So once we have this interaction, this benzene ring can be close to the structure, and they can be trapped easily by the composite. And this one, redox, that I want to mention here and highlight it, it's a very novel mechanism that we got from the composite only. So what is redox? It's based on the oxidation and reduction. And we couldn't measure, but we see the very low amount of low molecular weight polycyclic aromatic hydrocarbon remain in the soil. So it means that they haven't leached, but they have been oxidized and degraded, and the benzene ring has been opened up. So we just propose that we can have an advantage of redox reaction as one of the possible mechanism that we have during this amendment of the metal organic framework with biochar. So it just concludes my presentation. I really thank to all of you to listen to my presentation, and I'm happy if there is any discussion or question available from our audience.
Dear Dr. Mazarji, thank you very much for your talk. So do we have any questions? So I cannot see anyone, but I have a short question.
Yes.
So could you please tell me how these materials are used for soil or bioremediation? So do you put the powder to the soil, or how does it work, and how you collect them?
We mix first. We take the soil and we add different dosage of the composite inside and mix them, and then we start incubating them for 2 weeks to just see that if they don't have any interaction before. So we just let them to have a equilibrium. By the time then we transfer inside that a small leaching column. That's it. Unfortunately, we couldn't separate them, because if we had a chance to separate them at the end of the reaction from the column, we could get a better surface information. We could have at least XRF, different surface like an NMR, and see what's going on exactly. That's why we just propose the reaction mechanism, not be able to confirm the reaction mechanism.
See, and if you make a magnetic composite with magnetic nanoparticle in this MOF, can you then separate it?
Yes, Mikhail, this is our next step. We want to make them magnetite. We already order, and thanks to Professor Soldato for supporting our group for this project. And we already thinking to make them magnetite and separate them from the soil and see really what's going on deep inside the surface of this metalorganic framework. So we can publish high quality papers by not only proposed mechanism, we can confirm the real mechanism that we have during the reaction.
Okay, thank you again. Really nice talk and really interesting topic. I think that this ecological topic is really important, and I hope you good luck in your research. And so let's thank Mahmoud again. And we are going, so a short announcement. Now we have a talk just after this talk, and I sent the link to our chat. And so after this talk, we will have a long break until the next session. So we have only one talk left from Daria Trushina, and let's switch Zoom session.